The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today, what we're going to do is we're going to finish off our discussion about oscillators. In particular, we're going to talk about alternative designs for oscillators. So rather than having these loops that are purely composed of negative interactions, negative feedback, instead we're going to talk about cases where you have both positive and negative interactions. All right, so in using this kind of combined network structure, you can generate what are known as relaxation oscillators, which have some wonderful properties. In particular, you can get more robust oscillations relative to the parameters. But also, you can the oscillations become tunable, i.e., you can change the frequency without compromising, for example, the amplitude of the oscillations. Right? So for many both natural and synthetic oscillators, these so-called synthetic oscillators are perhaps the way to go. Right? Then we're going to transition to more of the global structure of some of these networks in the context of transcription networks within cells, and discuss this paper that you guys just read, the BarabaÄÅsi paper, which is one of the world's most cited papers, I think. Right? And then after thinking about this global structure of how you might be able to generate these so-called power law structures, we're going to look a little bit more detail to try to understand something about these network motifs. We've already talked about them a little bit in the context of autoregulatory loops, but now we'll talk about them in a little bit more generality, in particular in the context of feed-forward loops. Okay? And then on Thursday we will get into some of the possible beneficial features of feed-forward loops. On Thursday we talked about the repressilator. Right? So if you have X inhibiting Y, inhibiting Z, coming back and inhibiting X, that this thing it's reasonable to expect that it might generate oscillations. Right? And indeed, in the Elowitz paper that we read, such a synthetic circuit did indeed generate oscillations. But there were perhaps a few problems there. Right? So one is that only about 40% of the cells actually oscillated. Right? Who knows why not? Right? But also there were other problems that the oscillations seemed rather noisy. There was relatively rapid kind of desynchronization. Moreover, if you go and you ask, well, is it possible, or how easy would it be to change the period of the oscillations just by changing something like the degradation rate? What you'll find is that the oscillations are not very tunable. Okay? So I'll say the period or the frequency is not very tunable. Okay? And indeed, this is a general feature of oscillatory networks that have purely negative interactions. Right? So we talked about a couple of these cases. So for example, you can get oscillations just with negative autoregulation. And what is it that's necessary? What's that? High coordination. You mean your cooperativity in the repression, right? So that I think is necessary, but is it sufficient? Right. I mean, even in this case where I just have, let's say that I say, okay, x dot the rate of production. If this thing is just as a function of x, the sharpest it could be, right? This is kind of infinite cooperativity, so it's maximal expression. Then when you get above some x critical, all of a sudden you fully repress. Okay. If I just have this be the formula, do you guys understand what I'm referring to here? Right? Would this generate oscillations? So it actually doesn't. Right? So if in the simple equation where if we have x dot is equal to this function, so I guess this is a theta. I want to make sure I get this x less than x critical. That's what this means, right? So with some rate beta minus some alpha x. Does this thing oscillate? No. And we had a simple argument for why it did not oscillate as well. Yes? All right, we can yell it out. Somebody that was, I'm sure somebody was here on Thursday. That's right. So this is just a single. This is just an x dot. There's no x double dot. Right. So that means the derivative of x is single valued as a function of x. That means that we can't get anything that looks any oscillation here. Right. And then remember we analyzed this model where we explicitly included the mRNA. Right. So then we just had that x comes, and what it does is it represses expression of this mRNA for x, and then this mRNA comes back and makes x. Right. And in this model, was this sufficient? Did this give oscillations? No. Right. So here there was no oscillations. Again, here there were no oscillations. But I did tell you that there was something that you could do something more to get oscillations just with a single protein repressing itself. Right. So you need more delays. Right. So if you add delays, then it's possible to get oscillations. Okay. All right. So those delays could be in the form of having a model where you explicitly take into account that first the mRNA is made, and then that goes, and then you translate that to make some monomer, and then the monomer has to maybe fold, and then the folded protein maybe has to dimerize in order to do repression. Right, so if you have a more detailed mechanistic model that includes all these steps, that kind of introduces some sort of delay, that in principle can lead to oscillations in such a circuit. Or if you want to, you could just explicitly put in a delay. Right, so you could say that x dot, instead of being a function of x, right, instead what you can do is you can say, all right, well, it's actually a function of x at some time t minus tau. All right, so instead of having the rate of production of x be a function of x at that moment in time, instead it could be a function of x at some previous time. Doing that, that's a very explicit form of delay, and that can also be used to generate oscillations in a simple negative autoregulatory loop. Okay. All right, so these are all different kind of approaches for encoding delays into a model, and various approaches will give you oscillations. Okay. Yes?
Question for the repressor.
Yeah.
When you say the period is not tunable, it's because the mRNA lifetime is very difficult to.
All right. So when we say
in the model you can just.
Yes, that's right. So in the model you can in principle tune it. So what I mean when I say this is that in this class of model, so you can also have, instead of this repressilator with 3, you can have the so-called pentilator, where you have 5 proteins and each is repressing itself, right? So these are all have similar features. They all have like these odd numbers of proteins going around and repressing one another, right? And so you can write down the model with 7 if you want, right? But in all these cases, it's not tunable. What we mean by that is that when you tune the frequency, you, in general, lose the amplitude of the oscillation. So the amplitude will go down. Right? And there's, I think, a very nice paper that was written in 2008 on this topic, written by Jim Farrell at Stanford. All right, so I just want to mention this. OK, so it's Farrell at Stanford. This is a paper in Science 2008. And and it's called Robust Tunable Biological Oscillations from Interlinked Positive and Negative Feedback Loops. Right? It's a nice title, right? I like titles that say something, right? So it's sort of an ultimate short version of an abstract, right? If you can do it, I recommend it. Incidentally, in graduate school, I once wrote a paper with 4 words, short words: DNA overwinds when stretched. Right? Nice statement. Okay, you may or may not actually know what I mean by that. But it's a nice short title. It's a statement, right? So I encourage you to think about that when you're writing your papers. Okay. All right. So Jim Farrell, he wrote this paper where he said, all right, well, oscillations are really important, right? If you're thinking about the context of heart rhythms or cell cycle or this or that, right? So oscillations are important, but if you go and you look at the circuits that are generating oscillations in biology, they often have so-called interlinked positive and negative feedback loops. All right, so there are many cases where you have some x that actually is positively, it's kind of activating itself. Right? And this is very much something that will not lead to oscillations on its own. Right? It might be bistable. which is interesting, but not oscillations on its own. But then there's also maybe a negative feedback loop through another protein. And the idea is that this one somehow operates, this one's fast, and this one's slow. Right? And the key feature of these relaxation oscillators is that there are two time scales. Okay? And it's the slow time scale that specifies the period of the oscillation. And this fast one kind of locks the system into these alternative states. Right? So and this helps maintain the amplitude because it has this nature of being bistable. Right? So it's on or off. Okay, so this helps you maintain amplitude. All right, so this is kind of in charge of amplitude. And this one over here is in charge of the period. Okay, so what you can imagine that by changing this time scale, you can change the period of the oscillation, whereas this loop allows you to maintain the amplitude. Okay, and what Jim's group did computationally in this paper is they analyzed many different circuit designs that can lead to oscillations. And they showed that for the loops that are made of purely negative interactions like this, if you change a parameter in order to change the period, you'll also, in general, make the amplitude of the oscillations will drop dramatically. All right, so that's the sense in which they're not tunable. Whereas if you have this kind of design, you can actually tune over, in some cases, a very wide range, but maintain the amplitude of the oscillation. Okay? And in addition to being tunable, these things also end up being robust in various ways. Right? That the oscillation is maintained subject to various kinds of, if you twiddle with the parameters, you double this, you have that, you can still get nice oscillations here. Whereas in those designs, you tend to lose the oscillations more easily. Right? So they claim that based on that these might be more evolvable. Okay? So even in cases where you don't need to tune the period, maybe you still end up evolving towards this design just because it's robust to stochastic fluctuations and the concentrations of things, but also it might be easier to evolve these sorts of oscillations. Okay? Are there any questions about the kind of intuition behind this for now? There's a nice kind of circuit analogy that people often talk about in the context of this. Sorry, so if you imagine you have some battery with some voltage V, we'll say V battery, all right? Some capacitor over here, all right? But over here you have something that will spark at some voltage, some VT. You get a spark, all right? Now the question is, well, what happens over time if V threshold is less than V battery? Okay, so we maybe should have a resistor in here for. So if V threshold is less than V battery, then this can generate nice oscillations in the voltage, say, across the capacitor as a function of time that are tunable, right? Because if you plot as a function of time, this is the voltage across the capacitor, where up here we might have the V of the battery. Here we might have V threshold. Okay? Now, in the absence of this thing that's going to short periodically, we're just going to charge up the capacitor. Right? So in principle, there's going to be this standard RC time constant coming up to here. Right? But before we get there, we get the spark. Right? So then we discharge across here, and then this drops. Right? So you get something that looks like this. All right. Now you can imagine by changing, for example, the resistor, you can change the rate that the capacitor will charge up. Right? But the amplitude of the oscillations stay constant because that's set by the voltage threshold across this where it shorts. Okay? All right, so this is capturing this dynamic of the separation of timescales. Right? So there's a slow timescale, which is this RC time constant, and then there's the rapid timescale that is where this shorts off. Okay? And so you can imagine that this is an example of an oscillatory signal that we can tune the frequency without sacrificing the amplitude. Right? right, so what we've said so far is that there are engineering analogs to these sorts of relaxation oscillators. We can model various synthetic circuits, or we can look at natural oscillatory networks in order to get a sense of what's going on. Right, but of course, a major goal of this kind of system synthetic approach to the field is that if all this stuff is really true, we should be able to build it, right? And there's a very nice demonstration of this also in 2008 by Jeff Hasty's group. All right, so Jeff Hasty was actually trained as a high energy theorist, and then I guess it was during his postdoc, maybe switched into experimental biology, went and did his postdoc, I think, with Jim Collins, and then eventually now has his own group doing systems synthetic biology. All right, so in this paper, it was a Nature paper in 2008. It's called, again, a fast, robust, and tunable synthetic gene oscillator. Right? It's a nice statement, tells you what he's about to do. Right, but the data here, so this is, again, it's using this basic insight of having both interlinked positive negative feedback loops. In E. coli, he demonstrated that he can get really beautiful oscillations in essentially all the cells, and that they're tunable in period by a factor of 3 or 4 or so, right? So by a fair amount, and indeed as fast as 13 minutes, the oscillatory period, right? Which is pretty nice, right? So I encourage you to check out this paper. This paper was also an example of how it was in principle possible to get oscillations just by doing negative autoregulation. Right, so this was a case where they designed a gene network that they could tune and had this wonderful property. But then after they did that, they noticed that in their model at least, they could get oscillations in some parameter regime just by having a negative autoregulatory loop. And as a result of all these intermediate processes of protein maturation and so forth, and they went and they constructed that network, and they showed that that could also oscillate. Right, so again, this is an example of the interplay between modeling, experiment, theory, modeling. And Jeff Hasty has gone on to write several really beautiful papers looking at these sorts of oscillations, looking at how you can get synchronization of oscillators, and you get period doubling ideas. It's really a whole string of wonderful papers. So I encourage you to, if you're interested in oscillations, to look at Jeff Hasty's work over the years. And if you want to a quick introduction to these papers. I also wrote a news and views in Nature on these 2 papers, so you can read that. It's only a page. So that's, although I guess you won't hear anything that you haven't already heard, probably. Yeah. Any other questions about this idea of how we can use both positive and negative feedback in order to get some nice oscillatory properties? OK, then let's move on. All right, what did you guys think of this paper, the BarabaÄÅsi paper? Good, bad, difficult, easy? Why does it have so many citations? All right, that's and you should look at how many. I mean, according to Google Scholar, I haven't checked this year, but it's probably like 20,000 citations. I mean, it's. It's a cult thing. Well, I don't know. That might be exaggerating. I mean, it's a nice paper. Yeah, right. All right, so this is interesting. I think that the basic answer is that there are networks that are relevant in many, many, many fields, which they allude to. And there are many researchers that have been excited about studying those networks in many, many fields. And many, many, many of the networks that are observed in nature, social science, the web, everywhere, they have these power law structures, and this is the first clear, simple mechanism to generate it. My understanding is actually that that actually a mathematician decades before actually did demonstrate that this kind of thing could be constructed that would lead to this, but that paper doesn't have 20,000 citations. I mean, like, it's a lot of these things. You have to be at the right time, the right place, and have the right idea, and
Yeah, I guess my main thought about the paper is exactly that the interesting thing about it it came out at about the time that data on large networks was really available.
That's right. Yeah, there's a reason that this paper was published at this time, and and of course, if BarabaÄси didn't do it here, someone else would have done it a year or two later, right? But it was really that the data were available everywhere, and so then and we were seeing these power law distributions, and it's really crying out for an explanation. Okay, I think it's and sometimes people complain that they say, oh yeah, I could have come up with this idea, it's not that deep, and yeah, maybe you could have, but but you didn't, and also I'd say that BarabaÄsi has a record of doing interesting things and being the first to point out a simple idea, and if you can reliably be the first to point out a simple explanation for important things, then that's another kind of genius, right? I mean, and it's the kind of genius that I would I aspire to, because I know that I'm not going to reach the other kind of genius, right? So there are some things that you look at and you're like, oh well, I would never be able to do that, right? And those everyone agrees that that's hard, but I think that there is something about being able to see what the scientific opportunities are at a given time, and you don't have to come up with a really complicated model or proof in order to have really important impact. And this paper is way beyond, in terms of like number of people that have read it, cited it, and so forth. It's way beyond probably any other paper you'll likely read in your life. Okay. Yes.
Just more thoughts.
More thoughts. Yeah, that's fine. Yeah.
Okay. I mean, I guess what's interesting is, it starts a conversation. It's like we can analyze these networks, and this is a feature that's worth investigating. Is still there. So it starts that conversation. I think there's still a lot more that we can do with it, and he's done more. I think that's why I like it.
Yeah. No, I think that's a totally. So this is the BarabaÄsi and Rika Albert. So BarabaÄsi is a professor over at Northeastern now. Rika Albert is a professor at Penn State, and I think they've both gone on to do what I think are really very interesting things, in this network space, but and more generally. So I encourage you to check out what each of them have been doing over the years. All right, so this is this model. Okay, what are the two key ingredients of this model?
Growth and preferential.
All right. So the two things that you should be able to recapitulate on an exam is that there are two assumptions here. There's growth and there's preferential attachment. Okay? And we'll talk about the degree to which we think each of those things might be necessary. But what's the key? Yeah, can somebody be a little more explicit than what we've been so far about what the key kind of observation is that we're trying to explain?
There are nodes that in a network that have way more edges than you would expect, either by random or...
Right, perfect, right. Observation, all right, so some nodes have lots of edges.
I mean, it is kind of a meta-irony that this paper now is very widely cited. This
Yes.
will be stated every time we talk about the paper.
Yes, it indeed it is. It is ironic, and we'll talk about how the scaling of the citation networks go in a moment. Right, so some nodes have lots of edges. All right, and then you want to be very clear about this. This is what you're trying to explain, right? So it's a power law distribution, right? So that in particular, you can quantify this thing, right? That the probability of having k nodes, the probability that a node has k edges falls off as a power law, 1 over k to some power 2, 3, 4, right? So the probability having k edges goes as 1 over k to some power alpha, right? Where alpha is kind of, maybe between 2 and 4 for a lot of these. Okay. Now, it's important to make sure that you keep this qualitative statement in mind, though, right? Because it's true that it falls off, and sort of rapidly, right? 1 over k squared, k cubed, or k to the 4th. You'd say, oh, that's a pretty rapid fall off, right? But it's not rapid compared to what? Exponent, right? So for these other models, then it falls off exponentially, right? So even faster, okay? So it's easy to kind of look at 1 over k to the 4th and think, oh, that's a fast fall off, right? But just we have to remember that it's slow compared to some other things, right? So in particular, if you look at the data for real networks, right, you see that the probability distribution in many cases goes over orders of magnitude in terms of this probability, right? So you think, oh, that's a big range, and it is a big range, but the fact is that you actually see some nodes with the 1,000 edges or whatnot, right? Which is something that you would just never see if it were a random network or if it were not a power law distributed network. Okay. And I think that this is also highlighting another statement, which is that a powerful way to make a difference, for example, if you're going to write down a model or you're going to do theory, is that it's nice if you start, if there's a clear observation that needs to be explained. Okay? Because you can always write down a model of something, and maybe you'll find something interesting, right? But a way to, I think, massively increase the probability that you're going to discover something interesting is if you already know there's something interesting there and that you're trying to explain it. Okay? And I think that this is an example of that, right? There was already an observation. It was already known, right? It's not that he was the first person to make those plots, right? There were other plots of citation networks before, right? So Sid Redner, for example, had already done some analyses of citation networks over, he's a theoretical statistical physicist over at BU, but just now, I guess, moving over to the Santa Fe Institute. Okay, but so it's not that he was the first person to make that observation, but he knew that he knew there was something interesting that needed to be explained, right? So I'd say that whatever, for any of you that are thinking about doing theory or writing down models, I would say, whenever possible, start with an interesting observation. All right, so can somebody, maybe you guys could just throw out, what are some examples of nodes and edges that were given there or elsewhere?
Web pages and links.
All right, web pages and links. All right, and is this a directed or an undirected? Yeah, so this is indeed directed. Right. Some others? Movie stars and movies. Yeah, this one's a funny one, right? Okay, yeah, so movie stars. And then, right, and this is like being in a movie together, right? So co-starring or so. All right, others? Articles and citations. Great. Articles, citations. All right, and this is, again, directed, and this is not directed, right? And we can maybe even try to remind ourselves, this fell off as alpha was equal to what? I guess it was 3, I think they said. All right, actors were around 2.3, I guess they said. All right, the web was 2.1. OK, all right, so just because it's a power law doesn't mean that it's always going to have the same alpha, right? But for example, what this means is that for every paper that has, say, 200 citations, there are going to be roughly 10 papers that have 100 citations, right? Because if you increase k by a factor of 2, you get almost an order of magnitude in terms of the probability distribution, right? Okay. All right, so this is an interesting observation, and where BarabaÄси came in and said, all right, well, what would be a model that would recapitulate this? Okay. And what are the models that did not recapitulate it?
The random networks,
Right, so the Erdos-Renyi. OK, so other models, right? There was the ER, other models. There was the so-called Erdos-Renyi network, random network. right? And that's because here the degree distribution is peaked around something and then falls off exponentially as you go above that. And this is actually where I think the equations are wrong in this paper, because if you look at the paper, page 510, right, they say the Erdos-Renyi, you connect the edges with probability p, and then they say you get a Poisson distribution, p of k, where lambda, the mean, is something. But then they say, oh, lambda is equal to some binomial something of k, and so forth. So I think that this is all not true, but rather that you can approximate the binomial with a Poisson in the limit of small p's. Okay, so beware if you're looking at that. All right, there was another network that oh, do you have a question?
No.
All right, so we're going to spend a lot of time talking about probability distributions in the coming weeks, but I just wanted to highlight that there is, as far as I can tell, that is not true what they say. Okay. All right, but there was one other model for a network that they talk about or they mention. Does anybody? The so-called small world network, right? And this is small world network. And this is based on a paper by Strogatz and Watts and Strogatz. Okay, small world. That's Watts and Strogatz. Right, and this was a paper where they demonstrated that there was a very simple mechanism just by kind of like rewiring a network that you could get this so-called small world phenomenon, right? Where the Kevin Bacon thing, where you can take from Kevin Bacon, and this is actually the actor network, right? So you can say, starting with Kevin Bacon, can you construct a list of actors that co-starred with each person that gets you to any given actor? And the statement is you're supposed to be able to do that from a path of 6, right? So that all the actors are supposed to be connected to Kevin Bacon by 6, right? Although maybe you guys don't even remember who Kevin Bacon is anymore. Is that? Oh, you do? Okay. All right. But this rule works for anybody. So just insert your favorite actor into that sentence. Okay. And it's important just to mention that just because something is a small world network does not mean that it has power law distributions. Right? It may be the case that many power law networks also have this small world character, and I'd say maybe even most of them, right? Because some of those highly connected nodes are going to be useful for connecting anybody to anybody else, but that's not required to get the small world character. Okay? Any questions about that statement?
So you can't go from this small world statement to any sort of strong statement concerning connectivity?
Well, I guess the strong statement is that that this property does not imply that property, right? I guess, yeah.
And you're not saying that the inverse is true either.
Yeah, and that.
It seems like at least the examples we've listed ought to be small world.
Yeah, no, I agree. I think that this small world property, that's why I was saying that it's, okay, what I do not know is whether it would be possible to construct a power law distributed network that does not have the small world property, but what I would say is that the ones that I'm aware of would have the small world property, right? Any other questions about where we are? All right, so there's interesting properties of networks that we would like to explain. Right? And I would say that what this paper does, I think kind of convincingly, is that they demonstrate that at least this model, and we'll get into the assumptions, does lead to a power law distributed network. Okay? Now, in the there was the answer to the reading questions about whether both of these is strictly necessary, I think was an interesting one, right? And I'd say that this gets into the wider issue of there's an observation that is maybe interesting, okay? And then we want to understand why that might be, and then what you can do is you can write down a model that leads to that behavior. Okay, we've already talked about this. Does that prove that the assumptions of the model are correct? No. In this case, these are pretty generic features of lots and lots of the network. So I'd say when you read it, you kind of believe that this is a dominant mechanism, but it very much does not prove that these are the only. This is not at all the only way to get a power law distributed network, right? And I'd say that some of the language in the paper might kind of lead you to believe that that is the case, and I think that that's, this is a standard logical fallacy that we have to be careful of, and I think that some of the language is a little bit dangerous, so the development of the power law scaling of the model indicates that growth and preferential attachment play an important role in network. I would say that I think it's probably true, but but once again, it's a question of this is certainly not a proof that those assumptions are relevant for any given network. Of course, in all these cases, the network does grow, and there is preferential attachment. But it's also there are other things that are also true that may be important. For example, in determining exactly what alpha is, or in other things. And I think that, as indicated, that there are other ways of getting power law networks without making the exact assumptions that are here. But I think it's in my mind probably a or the dominant mechanism in a lot of these networks. So I think it's a fine paper, but just remember that it doesn't prove that those are the only two important things, right? Yes.
Just about the preferential attachments, I think you mentioned that we tried different
Yes.
ways, and only the linear one.
Yeah. This is
Which is
troubling.
well,
Yeah. No, I agree. Right. So right, and what they assume in the model here is that the preferential attachment goes linearly with the number of existing edges, right? And I would say that I very much believe that preferential attachment is present in all those things, but I'm sure that if you go and you measure it, you're not going to find that it's linear with the number of edges. It's going to, I don't know what you'll find in each of those cases, but there's no reason to believe it has to be linear. Right? That being said, it may be, the question is how strong of a deviation from linearity is there, and then how sensitive is the power law behavior to that, and that's the kind of thing that I'm sure that one of the 20,000 papers that have cited this paper in the last 15 years address this issue, right? But this is also why there are so many papers that cite. It's like you read this paper, like, it would be really interesting to do this, that, and people have been following that interest, right? Okay, let's go ahead and, I think that the derivation is a little bit tricky. So I think it's worth, just walking through it. Especially since some people apparently couldn't even get the equations, which are going to be is going to be a problem. Oh, and maybe while we're on this question of preferential attachment, how do you guys feel about this question of networks within, say, the transcriptional network of E. coli or other cells? Do you think that these properties are relevant in the cell, or? Right. So what would growth mean? Right. So growth would correspond to adding a new gene. Does that ever happen?
Yeah.
Okay. And what can someone give a possible mechanism by which a new gene is added to the genome? Right. So for example, duplication is common, right? E.g., duplication. And so what does this mean for preferential attachment? Sorry, my phone is up.
If we duplicate the gene, then we'll probably also duplicate the promoter region, which means the
Yeah.
protein is still
Right. So this, I think, is very interesting. Right. So duplication, in general, you'll duplicate both the coding region that makes the protein, but also maybe the promoter region that specifies the regulation. Right. So if you imagine you have some x here that is, right, and we can remind ourselves, are both the incoming and outgoing edges power law distributed in transcription networks? No, I know this was in this was the pre-class reading, but just in case, right? So what you find is that some transcription factors regulate many genes, but we don't have any proteins that are regulated by 200 genes, right? So in that sense, typically, right, we have things that are regulated. There's maybe some x1, x2, x3. Right? And there might be a few incoming edges. Right? So expression of a gene is typically specified by a few transcription factors. Right? Whereas some transcription factors might have 100 outgoing edges. Okay? So it's the outgoing edges that are power law distributed, and the ingoing are closer to being kind of Poisson or so. All right? So you can imagine that we have this guy might have 100 or so, and whereas over here some Y transcription factor that is just regulating 2 genes, say Y1 and Y2. Okay. Now, the question is, if gene duplication occurs kind of randomly throughout the genome, which target, or which transcription factor, X or Y, is more likely to have a target that's duplicated? X. All right. Interestingly, how does that scale with the number of targets? This actually is linear, right? So I'd say that gene duplication does give growth and preferential attachment that is basically linear with the number of targets. It's interesting. I'd say I find this kind of observation quite interesting and compelling, and makes me feel kind of comfortable about this as a mechanism for some of the global properties. I mean, of course, there's no selection. There's no way to explain, the interesting network motifs and so forth here. But I'd say just in terms of some general properties, I think it's interesting. Of course, once again, not a proof. Evolution can do whatever it wants with these gene duplication events. But so I would say, not everybody finds this argument very, very compelling. But I'd say I think it's kind of, I get a warm, fuzzy feeling inside. Yeah.
So we're talking about the transcription network. It's different from the other networks we're talking about in that you also lose genes.
Yeah.
And so is there any discussion
Well,
about how that?
you can lose web pages. You can.
Are you losing them nearly as fast as you're adding them?
Yeah, I don't know. I find that lots of links to my web pages just disappear over time, and I don't know. It's a reasonable question. I don't. Right. In some of these you'd say, oh well, right. So the web has been growing a lot recently, and so then we'd say that birth dominates over death there. Whereas if you talk about genome sizes along different lineages, it certainly is not growing exponentially the way the web page. Yeah, I think that's fair and true. But we haven't really actually specified or made clear within a model what happens if you allow for birth and death, right? But I think that you could introduce death and recapitulating these behaviors. So it's not. I think that it's just because some nodes disappear doesn't mean that we have to throw the whole idea out the window. But evolution, in the presence of evolution, this is all very complicated, right? So you can't carry this argument too far. But okay.
So it's only linear if each gene has one promoter.
What we're assuming is that there's some segment of DNA that's in front of the gene that gives instructions of when to transcribe the gene. Right. So the linearity is just assuming that's really just assuming that genes have kind of the same rate of being duplicated on average. And this is a very global property. So I think that it's kind of roughly I would say it's the null model that you would use if you had to write down a null model. Yeah.
Is there any paper looking for evidence to support the idea?
Yeah, that's an interesting question. And it's hard to know what it would even mean to quite be evidence to support it, in the sense that you're saying along different evolutionary lineages, could we say that it's more likely to grow? Of course, the other thing to say is that the rate of death would also scale linearly. In the sense that if a gene being stochastically removed from the genome should also scale linearly, right? So it's not that you don't actually then expect there to be any systematic change. It's not as simple as just saying, oh, the number of targets of a transcription factor with many targets should grow faster. It's really that the expectation is that it should be changing faster because both duplication and removal would both be increasing. So I think the signature is not totally obvious in that sense. No. All right, so how many people actually tried to piece this derivation apart? Anybody? All right, and were you happy with it at the end of your ruminations?
An assumption near the very end that I was a little bit iffy.
Okay, yeah, it kind of, there is like a crux of the climb at the end. All right. Okay, so all right, let's just make sure that we can understand kind of what happened there, because it's worth, since we read the paper, it's worth trying to figure it out. All right. Okay, so what we're going to assume is that we start with m0 nodes. Okay, so they're going to be here, and the idea is it doesn't really matter how we start this thing. They might start out being unconnected, or they might be connected. And over time, the signature of how we start is not supposed to be that important, right? And then what we're going to do is, at each time point, we're going to add one more node. And as we do that, we're going to add m edges as well. Okay? Right. So we then have the number of, we'll say, nodes n as a function of time is going to be equal to what? All right. This is just going to be, we're going to start at m0, and it's going to be, we're going to add 1 each time. m0 plus t. Number of edges is just going to be equal to the number that we add each time point times the time. Okay? All right, so here we're assuming that we start out with these nodes being unconnected. Now, we're given the assumption that there's preferential attachment, right? So that means that the probability of connecting to some ith node that has k edges is going to be k to the I divided by the sum over all of the edges. Yes?
Why is t n times 2?
All right, so the assumption is that at each time point, we add a new node, let's say this node, and with that, we bring in some number m of new edges. All right, so this could be 3, and then we go randomly to 3 of the existing nodes. All right, so each time point, we add m edges.
You necessarily add them to the new node? Like you necessarily connect the node that you add?
I'm sorry, I don't understand. Oh yeah, right. So the assumption is that the new node is indeed being connected to right. That all m edges that we're adding are to this new node. Yeah. Okay. All right. So this is the linear preferential attachment that we were talking about. All right, so what we want to know first is how, after a node is connected, how is it that the number of edges will grow over time? All right. What we know is that when it's first added, it has exactly m m edges, right? So, but then as new nodes come, then we'll maybe get some more, and then it'll grow. Okay. And in particular, we want to get, we're told that it's going to grow as this differential equation. Okay. So we want to kind of get to this, right? And the way to think about this is that, all right, well, how is it that the number of edges will change at each time point? Some delta ki, right? Well, the expected number of edges that will be attached to some node, well, that's going to be m. This is the number of edges that were attached by this incoming node, and times this probability of attaching to this node. Right? So this is the probability of ki. Right? Now this is in one time step. Right? So this is really a delta ki. If we want, we could say over some delta t, which is 1. Right? So from that standpoint, we can actually then write it as a differential equation where you say the change in this number of edges with respect to time is indeed going to be equal to m times this guy here, which is the number of edges that node has at this time, divided by this sum over all those edges. Okay. All right, so this is just the kind of the expected number of edges to be added to that node at each time point. Okay. All right. So, but what is this thing? What is that thing equal to? Yes. I did.
Okay, but
yeah, no.
On the left side of that equation, you wrote it as the change in
Yeah, so this is kind of the discrete version of this differential equation.
Oh,
right.
That.
Yeah, that's right. Yeah. And of course, the beginning could be highly stochastic, right? But we're just thinking about it in the limit of if it's deterministic, right? Right. So what is this thing in terms? I mean, so from here, this was just a normalization constant, right? Because each edge has to be attached somewhere. We're assuming it's linear with respect to the number of edges at each node, right? And that means that for normalization, we have to divide by the sum over all those edges, right? The edges that each of the nodes might have. But what is this thing equal to in terms of something else that we might have on the board? Yeah.
Always have edges with respect to time equal to t.
Right. OK, so I guess the question is, well, can we write this? E, where E is a function of time. Is that correct? So we're getting some shakes.
Isn't it 2e?
Right, so it's actually 2e. Right? Because what you notice here is that this is the sum over all of the edges that each of the nodes have. Right? But each edge is connecting two nodes. Right? So the sum over all these edge distributions is twice the number of edges. Okay? Now, I would say as a physicist, working in biology, my general attitude is that a factor of 2 here, a factor of 2 there doesn't really matter. Right? But this factor of 2 actually is relevant because it ends up determining the scaling over time. Right? So this is, not all factors of 2 are created equal, and this is one that is worth paying attention to. Okay. All right. Does everybody understand why this is 2 times the number of edges, right? All right. K1 is equal to 1. K2 is equal to 1. Number of edges is equal to 1. Yep. Okay.
So that means we're in an undirected network. If we were in a directed network, then we would not have that factor of 2.
Yes. So we are indeed in an undirected. And I'd say in a directed network, you have to then be more careful about what you have to specify the k's in and k's out. So actually already, just by writing this, we've already assumed it's undirected because we haven't specified what we mean by k. Yeah. Okay. All right. we're here, but very conveniently, we already know how many edges there are as a function of time. Right? This is just equal to m times t. All right, so we get something that's very convenient, ki divided by 2t. Right? From here, we can we can solve the differential equation. Right? So this is what we wanted to show. Right? So the fact that we're doing partials doesn't really matter because it's just time here. Right? So it's really we have dki over ki is equal to dt over 2t. Right? So this 2 really, again, is going to make a difference because when we go and we integrate, we get the logs and so forth. Right? And so we get that ki as a function of time is going to grow with time with some constant c proportionality to the square root of time. Right? So if we didn't have the half, it would just be linear with time. Okay? Now, how do we know what c? In general, how do we get constants of integration in life? Yeah, boundary conditions. In this case, the initial condition. What is it that we know? Right. So what we know is that ki, so this ith node, when it's added at time ti, it should be equal to what? Yeah, it's equal to m. So when it's first added at some time ti, its number of edges is equal to m, because that's what we've assumed is that we add a node and we connect it randomly to m other things, so it has m edges initially. Right? So from this k of t, this is then equal to m times the square root of t divided by t initial. Right? Where ti is the time that the ith node was added to the network. Are there any questions about how we got there? All right. So I think that this is relatively straightforward. I think the part that gets confusing is this later part about the probabilities and kind of keeping everything straight. All right. So what BarabaÄси did next is he said, all right, well, what we're going to do is we're going to talk about the probability p. Right? Now this is an actual, honest-to-goodness probability. Okay? The big P is actually a probability. And that's as compared to a probability distribution, little p. And I'll put in a little curly here thing. So that's a little p. All right? This is saying if you want to get an actual probability here, then you have to multiply that probability distribution times some range delta k. Right? So if you want to know that the probability that some node has between some number and some number of edges, then you multiply it by that range. Right? Probability distribution. This is an actual probability. Right? And as befits an actual probability, we're going to say, OK, the probability that the ith node has k edges that are less than some value k. And remember, this thing is actually a function of time. We have an expression for ki as a function of time. It's equal to this. Okay, so we can solve and we can show that this probability is also the same as this other probability, that the ith node was added after some time t that can be written as this. Okay, so this is saying the probability that some random, say ith node, has fewer than k edges is the same as saying that it's the probability that the ith node was added after some time t, which is this thing. Okay? Because the number of edges will grow over time for each of these nodes. Okay? Do you understand the kind of conceptual statement that was made there? Yes? Any questions? All right, so the probability that this ith node was added after this time is also, of course, 1 minus the probability that it was added before that time, right? All right. Whereas time little t here, this is at the time that you're actually looking, right? So this is saying, oh, well, if little t is 100, for example, it's saying, oh, at that time point, after we've added 100 nodes, right, we want to say, all right, what's the probability that some random ith node was added before this quantity? And this is just, again, some other kind of time, if you'd like. OK, and I think this is the part that is especially kind of weird. All right, so this is also equal to this thing. And I think reasonable people can argue about exactly what you should write here. But let's figure out the basic argument first. All right, so this probability is equal to this thing. Okay, so the statement is really that at some time t, we have how many nodes? We have m naught plus t nodes, right? So this is something here. And of course, there are edges going around doing things, right? And what we want to know is, what's the probability if I grab one of them? And we're going to call that the ith node. Okay. So what's the probability if I grab one of them that it was added before sometime here? Okay. And it's useful to just imagine this as just being some time t, which will, just so that we don't get confused by all the symbols, right? And then you say, oh, well, that probability is really just the probability. Well, how many nodes total do we have? We have m naught plus t. How many nodes were there that were added before this time t? Well, that's going to be t. If you want, you might want to say t plus m naught. There's a question of whether you include those nodes that started there or not, right? Given the equations that BarabaÄси wrote down, he kind of assumes that we're only counting the nodes that were added later, right? But so I'd say if you want, you could either add an m naught up there or get rid of this m naught, depending on what you like, right? But broadly, there's this idea that we have this many nodes, and this many of them were added before some time t, and that's how we get this m squared t over k squared, which is just that time t divided by the total number of nodes. Okay. And this whole discussion about whether you count the initial m naught nodes or not, it doesn't matter, because we're going to be taking the limit as t goes to infinity, and that all goes away. Right. Yeah, are there questions about this? There's something kind of mind twisting about this argument, even though we're really just picking big T objects out of essentially little t objects, right? But somehow something funny goes on there. All right. Any questions about that?
Could you just go through the argument one more time?
Yeah, sure. Right, so I think that what's confusing about it is the fact that we're asking whether the ith node was added before some time t, and this time t is equal to something that's funny based on what we've just done. But I think it's useful to just ask if at time little t you have you look at this network, and I ask you, all right, well, was it added before this time big T? I.e., let's just, for concreteness, say, m naught is equal to, we start with 10 nodes, and we say, OK, at time t equal to 100, I ask you, what's the probability that if I grab a random node, what's the probability it was added before some time big T equal to 10? OK? Well, you would say, very roughly, actually, we can say let's actually, we can even just, if we'd like, say we're not going to count. We're not going to count those m naught initial nodes. So we're just going to be looking at nodes we added later, if you'd like, right? And then you would say, all right, well, at time t equal 100, we've added 100 nodes, right? And I'm asking you, if I grab one of the nodes, what's the probability that the node I grab was added in the first 10 time steps, right? Well, you would say it's going to be 10%, right? Because there were 10 nodes that were added before time big T, and we added 100. So it's really just this divided by this, and with the question of whether you want to include m naughts or not. Right? So I think that argument is surprisingly straightforward. But then somehow what gets really confusing is that the time t we're referring to, it's depending on the k's and the t's and so forth, right? But that's a way of keeping track of how everything is scaling as a function of time, right? But if you boil the argument down to this, then it makes sense. But then of course then you look back at this and you get confused again, right? Which is how I feel every year when I prepare this lecture. but I think it all does make sense if you. Okay. Any questions about this argument or that argument or any part of it? Yes.
So is Ti the variable here, or is Ti?
Yes. All right. So. Right. So okay. So this is Ti. This is just saying that if I pick some random node, we're calling it the ith node. I'm asking what's the probability that the time it was added was before something. Right, so this is not one of the variables, and you'll see that Ti doesn't appear down here, because this is just saying, because I'm asking you, if I grab some random node, the ith node, I'm asking you what's the probability that it was added before some other time, which is all this, right? So, and what you can see is that it's a function of the time that we look, right? Because if I go to longer times, then indeed this probability. Should it go, what should it do? OK, but it depends on k's as well, right? What do I want to say? Right, because ultimately what we see here is that as time goes to infinity, so after a long time, then we reach this stationary distribution where the base structure of the network is not changing anymore, right? And that's because there's a t in both the numerator and the denominator. So then the only thing that kind of is left is this behavior as a function of k, right? So this is really saying that the probability that some node was added before some time is kind of the same as saying that, well, that you have a lot of edges, right? And that's how we got here to begin with, right? Because the nodes that were added early end up with a lot of edges. This is the so-called rich get richer phenomenon, right? So if you're sitting on a manuscript and you're not submitting it for publication, you should kind of get on it, because the earlier that it's published, the more citations it's going to get. Okay, right? But this is saying that, right, the probability that some random node has a small number of edges is the same as the probability that the node was added late, right? And that makes sense, because if it's added late, it doesn't have very many edges, hasn't had time to grow, right? And then, it just from those calculations, you can get it at this degree distribution. Okay. Yes.
So in this analytical analysis variables, we're assuming that the links could be non-integral.
Yeah, OK, right. So yes. So we're taking, in principle, it's a discrete problem and converting it into a differential equation, right? And it's an interesting question of I don't know how big of an error this ends up making, right? And of course, this expression doesn't actually end up being having integers, right? But this is a way of making it so that the errors don't grow or so, right? So I think that it basically works. I think, and if you'd like, you can sit down and actually do the simulation with all the discrete. I think that it's actually going to be the stochastic dynamics that end up being more relevant than the integer kind of issue. But I haven't actually looked into that, though. OK. All right. Any other questions about that so far? All right. Yes.
You're not counting the case when we use.
Right, so there's no loss of edges, no loss of nodes, strictly verboten. I spent a lot of time trying to plan an upcoming trip to Germany last night, so German is on my mind. All right, so are we done yet, incidentally? Nearly, right? Because we have Now but what we really wanted is the degree distribution, not this probability. Right, so we have to take a derivative still. Right, but as t goes to infinity, regardless of how you treat the m naughts, actually, well, maybe we'll take the derivative first. Okay, so this probability density, right, is going to be the derivative with respect to k of the actual probability here. Right, so we take a derivative, this one derivative, nothing happens. K squared, it's going to turn into a k cubed, right? So we get 2m squared t over k cubed. We still have the t plus m naught, right? But when we let t go to infinity, so after this thing has reached its stationary distribution, then we end up just getting 2m squared over k cubed, right? I just want to be clear. This is to the k. Right? The key feature here is that the probability distribution goes as 1 over k cubed. Okay. What is interesting is that when I first read the paper, I actually thought that this exponent here would be a function of the linearity of the preferential attachment. So I actually, and of course they say that it's not true, right? But when I was halfway through the paper, I thought, oh, well, if you just let this go as some power to the beta or so, then you would maybe get something like, oh, this was 2 plus beta. I thought something like that. But apparently it's not true, right? That if you do not have linear attachment here, then you just don't get power law distributions, right? They suggest other ways that you could maybe get different exponents, which is very relevant given the fact that different real networks indeed have different exponents, right? But I'd say that their proffered explanation, which is to include directed edges, feels unsatisfying because not all networks are directed, right? And this network here is not directed and has an exponent closer to 2, right? So you really want to have other mechanisms. But this, as we've mentioned, it's a thriving field, and people have explored many different aspects of this problem. Okay. Are there any other questions about this derivation, how we got there, how convincing you think it should be or not be? Okay. So I want us to spend the last 5 minutes of the class kind of setting up the discussion of how we should be searching for network motifs. Okay. In particular, there's a natural question, which is we have to decide what the right null model is in terms of deciding kind of what the expected frequency of a network motif, like a feed-forward loop, might be. Okay. So first of all, why is it that we think that, why is it that we maybe should not use an Erdos-Renyi network? Yes?
It's not very good for handling directed networks.
Right. OK, so you'd say, oh, not very good. I can maybe make, there's a clear analog to you can take a random undirected ER network and say, put arrows randomly on each edge. I think that there's a natural ER version of a directed network.
There are constraints.
Like what?
When you replicate in a transcription network, when you do duplication, you don't randomly assign the edge. Right?
That's right. OK, so one thing is that it may be that biologically there are constraints. But that should manifest itself somehow in the sense that if all that may be well and good, it may be true what you're saying, but if we go and we look at a transcription network, if it looks like an ER network, then I would say it just doesn't matter, right? The fact that there's microscopic things going on. If at the end of the day it looks like an ER network, then then maybe it's fine anyways, right? Or maybe not. Yeah, you can argue either way.
If a particular, I mean, it depends on what you want. If a particular motif occurs a lot, it might be because of the, it might be because it's selected for evolutionarily, or it might be for some other reason.
That's right. Okay, so this is an important point that, right, I would say that in Uri's approach, he basically says, if we see a network motif more frequently than we would expect based on some null model, some null network, then it's kind of prima facie evidence that maybe evolution was selecting for it for some reason. Right? And what you're saying is that it could be that there's a microscopic mechanism that just leads to those things happening. And so it doesn't have to be selection. It could be just due to the mechanistic processes below. Right? And I think that's a fair concern. And it's related to a lot of these other things in that just, for example, duplication will naturally lead to something. I mean, if you start out with x regulating y, and y is duplicated, then now you have x regulating some y1 and also some y2. Right? And this is the beginnings of a network motif, right? And so it's a reasonable thing to worry about. But maybe we can correct for at least a majority of this by using the proper null model. At least that would be the hope.
Well, right, but that's why you don't want necessarily.
Okay, that's why you don't. Yeah. Okay, that's fair. But then the question is, what null model should we be using? Yeah.
So I feel like having the microscopic constraints does not necessarily need to be in the null model. I feel like we can have a null model without using the microscopic constraints and then just say, oh, well, that's another possibility for why we might have these divergences.
Yeah.
I don't think they need to be in the null model.
Yeah, it's just that then you can't say anything about evolution.
Well, fair, but I don't think you should have to be. I don't think you have to say something about evolution afterwards necessarily.
Yeah, and I think that this question about how strongly you can argue that evolution is selected for something, this is a little bit of a judgment call, because most of these evolutionary arguments are not ironclad. It's more a matter of making you feel, kind of comfortable with looking for what the evolutionary explanation might have been. And this is just, the nature of looking at, of historical science, right? You can speculate about what would have happened if Napoleon had done something else or whatever, right? But it's a speculation. Of course, the hope is that we can collect multiple pieces of evidence that make us more and more comfortable with it. In some cases, we can do laboratory evolution to get more comfort, right? But laboratory evolution doesn't prove that that's what happened, a million years ago either, right? But I'd say it's more the accumulation of evidence to make you feel comfortable with an argument. But let's first maybe make sure we understand what the null model is, and then we can and then on Thursday we'll decide whether, we'll discuss what we think that means about evolution. Yeah.
So I think the other part in the appendix that we read about the in and out distributions is important for the null model.
Yes.
Because it seems to me that the Edis-Renyi network might be a good model for the in distributions, but not for the out distributions.
That's right. Yeah, and I think this is really important. I think that it's clear that the actual transcription network of E. coli, for example, is not well described as an Erdős-Renyi kind of random network. But then it kind of does beg the question of what should we be using? And you could say, well, we just make a power law network. But then you say, oh, but there's the in degree and the out degree. How much do you want to keep track of that? And I think that there's a fairly strong argument that what you should do is what they call this degree preserving network. And in particular, what that means is that you take the real network, right? So you take the actual network that you're going to be analyzing. And there is some actual degree distribution, right? So there's, one node has, so K1 might be 106, K2 might be 73, up to Kn, which is equal to 1. And of course, I'm not even talking about it being directed, but you can do the same thing with directed, right? But then what you do is you kind of mix things up. So you start with the real network, and then you do something to randomize it. Right? And it's a rather clever scheme. I'm just going to describe it briefly here, and then we'll talk more about it on Thursday. What you do is you take all of the actual So let's say we have some x1, some x2, and some here we have a y1, a y2, y3. Okay. Now let's say that these guys are regulating something like this. What you do is you take two edges randomly. We'll pick this one and that one. What we do is we swap the targets. Okay. So what we do is we make this guy come over here, and then this one comes over here. Okay. So now what we do is we erase this, we erase this. Now we have a new network. But intriguingly, the degree distributions for both incoming and outgoing edges are identical to what we had before this. Right? Every guy has the same outgoing edges, incoming edges, but they have different targets. Right? So if you just do this procedure many, many times, then what you do is you achieve some randomized version of the real network. Okay? And then what you can do is you can ask how many feed-forward loops are there, how many this, that, right? And so I think that there's a fair argument that this is, in some ways, the proper null model to be asking the question. And indeed, for example, there are many more feed-forward loops than there would be in an Erdos-Renyi. But still, what you see is that you lose many feed-forward loops. So this is then the argument for feed-forward loops being selected for. All right, we'll talk about this and we'll quantify it on Thursday. But I'm available for the next half hour if anybody has any questions. All right.